Imagine a tiny, almost invisible crack, smaller than your fingernail. It's hiding in plain sight on something massive, something vital, and it's about to change an entire industry forever, silently. No explosions, no dramatic collapses, just a quiet, fundamental shift in how we build things. This is the story of train axles. Today, we're diving into the incredible story of train axles. These unsung heroes connect the mighty wheels of a train, bearing immense weight and stress, day in and day out. But deep inside their seemingly solid metal, a hidden enemy was at work. An enemy so subtle, it took a near catastrophe to reveal its true power.
So what exactly is a train axle? Think of it like a giant metal rod connecting two train wheels. It doesn't just hold them together, it's the critical link that transfers all the weight of the train cars and cargo down to the rails. It's constantly spinning, constantly stressed, and absolutely vital for safe travel.
Now, imagine the forces this axle has to endure. As the train moves, the axle isn't just spinning, it's also bending slightly. Each rotation means the top of the axle is in tension, pulling apart, while the bottom is in compression, squeezing together. This constant back and forth bending over millions of cycles is where our hidden problem begins. For something so critical, engineers naturally chose incredibly strong materials. For decades, high-quality steel was the go-to choice for train axles. It's tough, it's durable, and it can handle a lot of punishment. Or so they thought. The initial material specifications seemed perfectly robust for the job.
Historically, these axles were made through a process called forging. Imagine giant hammers shaping incredibly hot steel, compressing it and aligning its internal structure. This process was believed to create incredibly strong, defect-free components, perfectly suited for the demanding life of a train axle.
Beyond the core strength, the surface of the axle was also crucial. A smooth, polished surface was believed to be best, as any scratches or imperfections could act as stress concentrators, tiny points where forces would gather, making the material weaker there. So careful finishing was always a priority.
Despite all this engineering prowess, something strange started happening in the early to mid-20th century. Trains weren't suddenly derailing left and right, but engineers began finding tiny, almost imperceptible cracks in axles during routine inspections. These weren't just cosmetic, they were deep, growing, and incredibly dangerous. This brings us to a phenomenon called metal fatigue. Think of it like bending a paperclip back and forth. You can do it many times, but eventually it breaks, right? Metal, even strong steel, behaves similarly under repeated stress. It doesn't break instantly, but tiny cracks start and grow over time, even below its normal breaking strength. But these axle cracks had a particularly insidious twist. They weren't just simple fatigue. Engineers discovered a phenomenon called stress corrosion cracking. This means the crack wasn't just growing from repeated stress, it was also being accelerated by corrosive elements in the environment, like moisture and oxygen, attacking the stressed metal.
Here's where the subtle part comes in. The traditional methods for finishing axles, while making them smooth, sometimes left tiny residual stresses on the very surface. These stresses, combined with the environment and the constant bending, created perfect starting points for these deadly cracks, even in seemingly perfect steel.
What made these cracks so dangerous was their silent nature. Unlike a sudden break from overload, fatigue cracks grow slowly, sometimes over years, without any visible warning signs until it's almost too late. They propagate internally, hidden from view, until the axle's strength is critically compromised.
The big aha moment for engineers was realizing the problem wasn't necessarily the strength of the steel itself, but how its surface was treated. The very processes meant to make it smooth and strong were, in some cases, inadvertently setting the stage for failure.
The brilliant solution, widely adopted, was something called shot peening. Imagine firing millions of tiny steel or ceramic balls at the axle surface at high speed. It's like a controlled hammering. This doesn't make it smooth. Instead, it creates a layer of compressive residual stress on the surface. Why is this compressive stress so good? Because fatigue cracks, especially stress corrosion cracks, struggle to initiate and grow in a compressively stressed environment. It's like giving the axle's surface a protective shield, making it incredibly resistant to those tiny, insidious failures. It effectively closes potential crack starting points. This led to a silent, yet industry-wide material specification change. Shot peening became a standard practice for train axles and many other critical components. No dramatic headlines, no big announcements, just a fundamental shift in engineering practice that quietly made trains and countless other machines significantly safer and more reliable. A true testament to engineering learning from failure.
So the next time you see a train rolling by, remember the hidden story of its axles. Remember how a subtle crack, understood through clever engineering, led to a simple yet profound change that affects millions of journeys every single day. It's a powerful reminder that in engineering, even the smallest details can have the biggest impact.
If you found this deep dive into material science and engineering fascinating, hit that like button, subscribe for more amazing stories from the world of how things work, and let me know in the comments, what other hidden engineering triumphs would you like us to explore? Thanks for watching.